आज Krishna, are you audible? Signature. Jay Krishna, are you audible? Have you joined? You are not audible to us.
Hello.
Yes, you are audible.
Yeah, your voice is kind of echoing.
Sorry?
No, I can feel the echo. It is echoing. Your voice is not audible completely.
That is not a fault at your end, it is echoing in the classroom.
What?
It is echoing in the classroom. Yeah.
Okay, yeah, okay. Yeah, hello. Hello. Hello.
Yes, you're audible.
Yeah, now your voice is clear as well.
Can you share your screen?
Yeah, just a moment. Like I have to share the YouTube link to my team. So within like 2 minutes, I'll share my screen.
We will share your screen to YouTube. You don't have to do anything. So your screen is being played. Your video will be played on the screen here, and on YouTube, your screen will be visible. So you just share your screen. That's all.
So when can we start the presentation?
We can start at 3 o'clock.
Yeah, sure. I'll wait.
Can you send me a brief biodata?
My bio.
Yeah, even on WhatsApp. Before the session starts, I will have to introduce.
Yes.
Send me on WhatsApp.
Yeah, sure.
Click on YouTube. That's and how it is. What will be telecasted to. If you want, you can switch on your camera. Whatever is convenient for you.
Yeah, hello.
Yes, you're audible.
Yes, yes. I have shared my bio, a small brief bio to your WhatsApps.
Okay.
Please check it. If it is, if you need anything else, just let me know.
Yeah, sure. Then we will come.
Yeah.
Sir, can you just put your slides in full screen mode once
Yeah.
for testing?
Actually, it is in full screen mode only.
Here we
No,
are not seeing.
yeah, it is not in presentation mode right
Okay.
now.
Okay. Yeah. Okay. Okay. Yeah, let me change it actually. Is it now?
Yes.
Yes, yes. Thank you.
Yeah. Hello, ma'am. Yeah. Yeah. Quick question. Like we have discussed for a 2 hour session, right?
Sorry?
No, we have discussed for a 2 hour session.
Yeah, yeah.
Yeah. What it is like in the meeting time is totally 1 hour only.
Okay, Google Meet, it is only for 1 hour.
Okay.
But it will continue, though it will not break.
Yeah. Okay then.
Jay sir, just I am
Yeah.
checking in YouTube. Can you speak once from your end just to check the YouTube link?
Yes. Hello. Can you hear me? Is it audible over there?
Yeah, yeah. Thank you.
Yeah. Hello. Hello.
So good afternoon all. This is the next session of this Gian workshop. And this session we will be demonstrating you the numerical tools for simulating photonic integrated circuits. And for this purpose, Jai Krishna K, he is an application engineer in ARC Info Solutions, which is currently the owner of numerical tools. So he has done his PhD on design and analysis of optical waveguides for sensing application. He has done his PhD from VIT Andhra Pradesh, and he has joined ARC Solutions in last year. So he'll be giving you a good demonstration of the tool, and we will be using this same tool. So actually, we covered it in the first half that we use these tools for simulating the circuit. So we will be simulating DP84 protocol and DPQKD protocol. These two on Wednesday we will have a hands-on session on this numerical tool in the lab, and at that time whatever features he is demonstrating we will be using it there. Okay, so over to you, Jai Krishna. Can you start?
Yeah, thanks for the introduction, ma'am. Hello, am I audible?
Yes, you are audible.
Okay, let's start the session. So, myself Jay Krishnan. So, I'm application engineer from ARC Info Solutions. So here I am to discuss about the numerical tools capability on simulating photonic integrated circuits. I'll try to cover as much as all the numerical tools that we are having. So without any delay, we'll start the presentation. So here are the agenda that I'm going to cover today. So it will start with a brief introduction to photonics as well as into the photonic integrated circuits. And so these numerical tools are by the leading engineering simulation platform called ANSYS. They are the numerical owners. So apart from numerical, we have other optics tool as well. So I'll give a brief introduction about them as well, and then we'll have a little bit discussion about a numerical and what are the numerical tools that we are having. Next, how can we do the a brief introduction to the photonic integrated simulation? So, and we'll be having two demos today, and we'll wind up the session with a case study. So before starting the session, like I would like to ask a question: what is a photonics? So in our everyday day-to-day life, light is everywhere. So the cameras on our phones, parking sensors in our cars, the monitors on our desk, everywhere we are using light. Without the light, we cannot see anything. So typically, like we can say, photonics is actually a multidisciplinary domain that involves generation, control, and manipulation of light. In other words, we can also say photonic is a field where the goal was to use light instead of electrons. How we are using electrons in electronical circuits. So we all know that light has a dual nature. Light will act as a particle as well as a wave. So it has characteristics of both continuous electromagnetic wave and particle called a photon. So most of the photonic applications are lies in the wavelength of UV2, visible and infrared, part of the electromagnetic spectrum. So this is a small introduction about this photonics. And next we will go into what is a photonic integrated circuit. So before we get to know about what is a photonic integrated circuit, we should know what is an integrated circuit. Integrated circuit is nothing but it's a collection of all electronics items like transistors, diodes, uh, resistors and capacitors, all stuffed into a tiny chip and connected to achieve a common goal. For example, we can say an operational amplifier. So these are on-chip material. So it will be fabricated on silicon, on insulators, and different fabrication methods are there. So technically, in an electronic chip, electron flux passes through the electronic components like transistors, resistors, inductors, and capacitors. In a similar way, photonic integrated circuit is nothing but it is an IC with photonic components. So what are all these photonic components? These photonic components are nothing but uh, these photonic components are an optical components which allow the photon to pass through them, like waveguides, lasers, polarizers, phase shifters, and these are the things. So so in PICs, we use a laser source to inject the light into the optical components. So then the light will be transported through these optical components, and they can, without any significant losses, and have a wide bandwidth, and for a particular common goal. For the specific application, we can do this. And also, using light instead of electricity in integrated photonic technology provides a solution to the limitations of electronics like integration and heat generation, and taking these devices to the next level. So with the inclusion of this PICs in the electronic integration circuits, we realize many new possibilities, which is so one of the possibilities actually, like we can say, the easiness of quantum computing. Quantum computing is already there even without the realization of this PICs, but uh, PICs made it faster. So, and the fabrication of these PICs is similar to the commonly made with CMOS fabrication technology as well. How we are making the EIC, electronic integrated circuits, in the same way we will be able to make the photonic integrated circuits. But electronic ICs are mostly made up of this silicon wafer. But in photonic integrated circuits, apart from silicon, we can use silicon nitrides, gallium arsenide is there, chalcogenic glasses, then like lithium niobate, we can use different materials have been used as well. And how these PICs works? So these PIC works on the principles of manipulating and harnessing the light for variety of functions. So which involves a photonic signal transmission from one end of the waveguide to the other waveguide, using different techniques like evanescent field coupling, total internal reflection, plasmonic activity. In a different way, we'll be using able to transfer the photonic signals from one end to the other end of a waveguide, and it will be having active and passive components. Each component will be having the, for example, if you're taking a resonator, it will act as a wavelength filters. If you're talking about a waveguide, the purpose of the waveguide is to transfer the light from the one end to the other end. So combinedly, they'll work together for to achieve a common goal. And these are some of the advantages of PICs. So miniaturization. So because light will operate in the visible wavelength, which is around 300 to 400 nanometer, so it will allow us to reduce the size, which is very much below than the conventional ICs. Higher speed, because light is very much faster than electrons. Low thermal effects and low power consumption, and also compatible with existing workflows like CMOS fabrication technology. And it will allow us to get the high yield and volume manufacturing. And some of the applications of PICs are sensing applications. So compact and sensitive sensors, temperature, pressure, chemical, composite detection, as well as in environmental monitoring, healthcare and industries also. PICs are people are using PICs, and in the medical field, for enhancing diagnostic tools as well as imaging and therapeutic devices. One such example that I can give is for cancer cell detection. These photonic sensors will be, we can use these photonic sensors effectively, and there are numerous research articles on that as well. The another thing is quantum computing. This is what our event discuss about in potential quantum information processing, as well as quantum state manipulation like qubits. We can able to generate qubits, qubits photon source, with the help of these PICs networks. LiDAR systems, which are these LiDARs are used in autonomous vehicle systems and as well as in military and aerospace. And spectroscopy, for used in chemical analysis, for material characterization, as well as in environmental characterization. Then military and aerospace. So in military and aerospace, like these PICs are used in communication systems, sensing technologies, as well as in imaging devices. Uh, why we are using these PICs in military and aerospace is because they are resistant to electromagnetic interface. Either the electric field or the magnetic field won't interfere the propagation of a photon. So it won't affect, it cannot be easily detectable, and it has high performance as well. And in general consumer electronics, displays, cameras, and wearable devices. So this PICs has a wide variety of applications. So now, since our, we are talking about this quantum computing. So how PICs are, good in quantum computing? PICs are very fast because of using the photons. Since light is having higher, faster velocity than electron, so it will increase the efficient quantum information processing. So enable manipulation of quantum states and photonic qubits for quantum computation. Next, scalability. So we can integrate multiple quantum components like waveguides, ring structures or whatever into a single chip, which will enable us to develop a large scale quantum systems and entanglement generation. So this facilitates the generation of entangled photons for quantum algorithms and communication, secure communication. So one such case is spontaneous four-way mixing, which is actually use this photonic components for generating this entanglement photons. Next, speed and efficiency, as we discussed, faster, energy efficient quantum gates with low power consumption, coherence and stability, and then quantum networks. So it supports quantum communication, entanglement based networking, as well as secure data transmission. So uh, now we have discussed about what are the photonics and photonic integrated circuits. Now, why do we need simulations? So, for developing this photonic integrated circuits, as we have already the CMOS fabrication compatible, so we can directly go for the right. So, why do we need these simulations before going into the fabrication? Because PICs are very expensive in R&D and hard to test a prototype. Technically, these photonic integrated circuits, developing these photonic integrated circuits to achieve a common goal is actually a iterative process. Uh, it's a repetitive process. So let's say if you're designing an optical fiber to transmit 5 gigabytes of data uh, with a very minimal loss. So you have to optimize it for the better performance. You have to change the core width, different materials you have to use. You have to use a different wavelength. So this is actually iterative process. So we cannot say that we will be achieving the optimal performance initially while developing the prototype. So these simulations will help us to reduce that, and it will cut down the cost because optical components are very costly to fabricate. Next, we can test and analyze the performance of the photonic integrated circuits, and we can predict the more accurate outcomes, as well as uh, we can multi-physics simulations. The one thing is, let's talk about solar cells. Solar cells is actually nothing but it is converting the light energy into the electrical energy, and also heat radiation will be there. So here it's a combination of heat, electron is also there, as well as photon is there. So this kind of multi-physics simulations is very much possible with the help of these simulation techniques. And if while doing the simulations, before going for the prototype, if we are able to identify the issue, so it will save us a lot of money. So early issue detection is very much possible with the help of simulations, as well as reduced prototyping, and it will increase the yield rate. So we can produce a more number of prototypes, or like the things that we want within a short span of time. So these are the reasons for us to leverage the simulations in developing these photonic integrated circuits. And in ANSYS, we have a complete system optimization of collaboration consolidation for developing a different kind of physics. We have different physics-based simulation softwares. Uh, here, for, here for structures, this is for mechanical fluids, for computational fluid dynamics. We have dedicated electronic simulation softwares for specifically for semiconductors, and we have optical softwares and 3D and photonic softwares. So all these softwares actually, multi-physics, which means let's say you have did something with the structures, and you can use this input, you can use the output of this one as an input in the optical. In a similar way, it will help us to create a complex models which involves multi-physics simulations. We can say CubeSat. So our ANSYS Optics suite, which offers a end-to-end multi-physics and optical simulation platform. So we all know that light behaves differently with different matters. It is a multi-scale platform. Like for example, we can say a light interacting with the nanomaterial is different than it interacts with the material of macro systems like lenses and mirrors. So in the larger level, like we cannot observe certain phenomena like diffraction, interference. But in the nano level, we will be able to observe many other phenomena as well, which includes plasmonic activity as well. We can observe. So for this multi-scale physics, we are having three different softwares. So one is ANSYS numerical, so which is our photonic design and optimization software, and we have this ANSYS Zmax, which is specifically for designing optical systems like lenses, mirrors, lasers, and we have this our optical system modeling and validation software. So this is our software specifically for designing lighting systems, ambient, outdoor and indoor lighting, as well as human 3D integration, and all kind of things are possible with this ANSYS POS. So totally we have three different tools, but here we are going to discuss about this ANSYS numerical for developing, designing these photonic integrated circuits. So, which involves two different type of physics. Whenever we are solving, technically these softwares are solving the problems using the method, employing the mathematical techniques as well. So here we'll be discussing about this wave optics and ray tracing. So I play this one. You can see the lambda is actually 4 and the material size is 20 micrometer, which means the order of the wavelength is almost comparable to the size of the material. So you can see a different phenomenon here, and look at this here. Now the wavelength is around 0.4 micrometer, which is 400 nanometer, and the size is like very much larger. So at that time, you can observe a different phenomenon, just a reflection. But here you can see scattering as well as it is refracting through this surface as well. So for this kind of simulation, we request numerical tools, which means feature sizes are on the order of the wavelength, so which accounts for reflection as well as for diffraction effects. But in the case of if the order size is very much feature size is very much greater than the wavelength. For example, if we are using the visible wavelength and the size of the materials are in the millimeters or in the meter size, we will be using the ray tracing. We'll be considering light as a ray, which means light will travel as a straight lines. But in the case of when the feature sizes are on the order of the wavelength, we'll be considering light will be traveling as a wave. So at that time, we have to use the wave optics. So this is a brief introduction of what is a ray optics. Ray optics is nothing but it's based on a straight line propagation of light, which deals with mirrors, lens, refraction, and reflection. So in the ray optics, we won't be discussing about some of the phenomena like interference, diffraction, polarization, which we cannot explain with the help of ray optics. So, so these ray optics are very well accounted for explaining the phenomena in mirrors, lenses, and lasers, where we are considering light traveling as a straight rays. And this means the optical suit that we are having Zmax and SPOs employing this ray optics technique to solve the problems. And wave optics. Wave optics is also a physical optics, but which will deals with the various phenomena other than the reflection and refraction, polarization, diffraction, interference, and other occurrences where ray approximation of geometric optics is not appropriate. So this wave optics here, we will be treating light as an electromagnetic wave. Generally, the numerical tool, what it will do is it will mathematically predict how the photons move through the space or a material. So we have four differential equations. So these Maxwell's equations are governing how a electromagnetic wave is propagating in a free space. So our numerical tools, especially numerical FDTD, FDTD is one type of a solver. So so numerical solvers will solve these Maxwell's equations to predict the how photons move through the space as well as how it is interacting with the material. So we can use this when the feature sizes are similar to or smaller than the wavelength of the light. If the feature sizes are larger than the wavelength of the size, larger than the wavelength of the light, at the time we have to use the ray optics. So who is numerical? So generally numerical is the industry leader for photonics multiphysics simulations, though there are like different other photonics multiphysics simulation softwares like Comm, synopsis. So Lumerical is the industry leader and is continuously innovated in demand solvers to complete their photonics portfolio for multiphysics. So we have this multiphysics feature, which is very much, and also we have partnered with Cadence and Mentor. For Cadence and Mentors are actually uh, electronic IC, analog and digital circuits development platforms. So this will the workflow integration with this numerical allow us to develop a complex PICs at ease. And we have partnered with many industry leading foundries like Compound Tech, TMSC, UMC for developing for PDK development. And when it comes to academic, numerical is considered as a standard solution. So that's why year by year academic citation is exponentially increasing. And this is our entire numerical solutions. So we have in a broad manner we can divide the solution into two types. So one is system soup, which is for photonic PIC circuit simulation, and another for component level simulation. In the component level simulation we are having different solvers, so which help us to model individual components, photonic components. And here we can able to develop photonic circuits. And apart from that, the HPC, high performance computing and cloud computing allow us to accelerate. As of now, we have FDTD and more. So we are also adding other solvers as well as the system suite as well. And we have other interpolatory as well as we can able to automate the program like simulation with the help of Python and numerical scripting. Numerical scripting is our own language model, language which is developed by numerical as well. And we have other tool integration as well, K-Layout, MATLAB, Tanner, which shows Zmax interpolatability. And we have foundry supports like Compound Tech, IMEC, Towser, Smart, and apart from this, many other foundry supports as well to easily develop photonic integrated circuits. And let's have dive into these different solvers we have. So FDTD, this is actually a flagship solver. So finite difference time domain electromagnetic solver. This solver is actually solving the Maxwell's equation for electric and magnetic fields in time domain at discrete position in space using a time stepping algorithm. So the propagation of electromagnetic wave is nothing but it's actually the oscillation of electric and magnetic fields in a perpendicular direction as well. So FDTDs will give us the most accurate results. So this is actually one of the widely used method for solving an electromagnetic problems as of now only. There are other methods like FEM, but FDTD is still now it is a widely used one, and it will help us to solve complex 3D and 2D geometries. So it will help us to give us a broadband results, which means like we can have a broadband spectrum, like starting from UV to the near infrared as well. And these are some of the applications like diffraction gratings, meta lenses, liquid crystal, metrology, LEDs, and image sensors as well. And next is within FDTD, we have another solver called stack optic solver. So stack optic solver is similar to FDTD, but this will help us to give us the solution particularly for plane waves incident on a multi-layer stack. For example, if you are talking about a Bragg rating or else like a distributed drag reflector. So at that time, you don't need a complex simulation. Just there will be reflection and transmission at the each interface. So for in order to solve those kind of smallest like simple structures, stack will be preferred because it is fast. It is a length dependent optimization. So you can optimize the length easily in this stack optical solver comparatively than FTTD, so which is much faster than FTTD. So we can record the transmission and reflection, and we have dipole illumination sources as well, and we can place multiple sources on multiple sites with the help of the stock optical solver. Some of the applications are lenses, anti-reflective air coatings, which involves like multiple film designs like you can see this, and multicolor filter and LEDs. And another one more solver is rigorous coupled wave analysis. This one complements FDTD and stack by providing a rapid simulation of light scattering for periodic and multi-layer structures, which is similar to that of stack only. But it is having only the plane wave illumination It doesn't have this dipole illumination, the other capacities that stack have. It is actually complementing these two solvers, so which can be slightly faster than FDTD. Both of those solvers like RCWA and the stack will be much faster than FDTD. So some of the applications are photonic crystals, meta lenses, diffraction gratings. And next solver is ANSYS numerical mode. Within mode, we are having FDE, EME, and variational FDTD solver. So when light travels through materials with different refractive indices, it can be guided. So mode has 3 separate solvers for different classes of waveguides. We'll be having different waveguides. We are not only having rectangular or like slab waveguides, we'll be having strip waveguides, slot waveguides. So for different type of class of waveguides, mode has 3 different solvers. Mode is actually a solver which will be specifically used for modal analysis and mode propagation as well. So we have FDE, which is a finite difference eigenmode solver. Using this solver, we can analyze the modes of 1D and 2D, modes of straight and bend waveguides, which is having a waveguide and which is a mode analysis software. And the next one is Where FDTD. Where FDTD is nothing but it's a 2.5D variational FDTD solver. So instead of using FDTD, you can use this variational FDTD solver for simulating some of the components like ring resonators and couplers. So these variational FDTD can be used for almost 90% of photonic component simulation. But this variational FDTD can be used as an alternate for FDTD for some of the components like ring resonators and couplers. It cannot be used when there is a vertical coupling. Let's say I'm propagating the light in xy direction, x-axis. Now I can observe the coupling in the z-axis. I cannot use this variational FDTD solver. Instead, I can use the FDTD solver. But if the coupling is like horizontally happening in the same plane, then we can use this solver. And what it will do is it will collapse the 3D planar waveguide geometry into 2D effective materials. Thereby, we can able to simulate this FDTD accurate simulation results with this solver as well. And this is a EMA, finite eigenmode solver, which is a mode expansion solver, which is very much suitable for long device. What it will do is it will break down a very lengthy component into a small pack components, and with that it will be easy. You can able to calculate the mode, do the modal analysis at each segment of a waveguide. You cannot do that thing with this FDE solver. And some of the application examples of this mode are bend losses, gradient fibers, tapered fibers, photonic crystal circuits, edge couplers, MIM couplers, electro-optic modulators, and plasmonic waveguides. So next is ANSYS numerical multiphysics. So which is one of the very important component. Here we'll be having 4 solvers. All these solvers are not using a different method called finite element solvers. So we have DGTD, which is a finite element equivalent of FDTD only. This is similar, which is almost equal for like for FDTD only, but for it is better for some specific applications. This DGTD employs different techniques for solving these Maxwell's equations, and it has limited sources and boundary conditions comparatively FDTD, but it is good for simulating a plasmonic applications. Next is finite element solver, which is actually a mode solver. So instead of using FDE of mode solver, we can use this FEM. And we have other two solvers as charge and heat. So charge is actually a charge transport solver. So it will look at the electrical properties of electrical charges as they move through the metals and optical materials as well as through the semiconductors. This is actually often used with the combination of FDTD. So light absorption modeled with FDTD, then the collection of generated charges modeled using charge. So this is actually a planar grating solar cell. As you can see, this one is actually simulated with FDTD. So light absorption we have modeled it with FDTD. Then collection of charges, generated charges we have modeled using charge, and we have plotted this VA characteristics of this solar cell, and we can observe this peak output electric power here. So with the help of charge, like the one perfect example for using this numerical multiphysics is developing a solar cell. Not solar panel, we have to be very careful, developing solar cells actually. Next, some of the applications are CMOS image sensor, LEDs, and avalanche photo detector, and heat. It's a heat transport solver. Unlike charge is an electron charge transport solver, and this is a heat transport solver. So some of the things that we can do with this, we can observe the conduction, convection, radiation, and Joule heating. And what the solver is actually doing is it will how is the thermal profile in a material altered when the material is subjected to electrical heating, which means when you are passing a current, as well as optical heating. What are all the change thermal profile is changing when it is absorbing the light. So one such example is the simulation of a planar silicon solar cell. So this they have simulated with FTTD charge as well as for the heat. So next is the multi-quantum well solver. This solver is specifically used for quantum mechanics. So quantum mechanics in the sense, like we know that it is little bit different than the classical mechanics. So we are the study of subatomic particles reveals unique and fundamental natural principles. So these fundamental phenomena, like some of these fundamental phenomena, where can be effectively simulated with this help of MQW solver. So it has a large material database of the group third to 5 semiconductors. Some of the strain, temperature, and electric field effects are included. We can able to analyze the band structure as well as it has wave functions, spontaneous emission, and optical gain features. These results are mostly used for compact laser models in interconnect. So the output of this one can be used as an input when we are developing a compact laser model in interconnect. So some of the applications are the active region of lasers and electro absorption modulator and developing micro LEDs. So with the help of MQW, this quantum well solver as well as with the charge integration. Uh, so these there is a new integration which is actually a new feature of the numerical, and the application is actually reverse biased electro absorption modulator and forward biased LEDs with the active quantum wells. So this is a complete workflow. As you can see, from components to circuits and systems with PDK centric flows. Here, this photonic multiphysics simulations, this complete solvers, these are component level simulation softwares. We can have the simulation data and we can import this simulation data directly into the interconnect, or else like we can able to develop our own custom model in this CML compiler, and then using these compact models we can able to create the structure and we can measure the data. So for the photonic integrated circuit simulation, we have a dedicated solver which is interconnect. So integrated circuit cell level simulated this one. So with the help of interconnect, we can able to uh, uh, you know uh, develop classical PICs as well as quantum PICs, and we can able to develop traveling wave laser model as well. So interconnect has a CML compiler, which is nothing but a compact model library. Compact model library in the sense, so this library will be having the individual photonic components, like in electronic ICs will be having transistors, resistors, diodes, right? So in the same way, this compact model library will be having different optical components. Not only optical components, it will be having analyzers, like oscilloscope and light detectors and sources as well. And we have Verilog A platform, which is actually a language which will help us to effectively model the photonic circuits with the help of this Verilog A language. It's a no, it's like a programming language. So this is actually the numerical interconnect interface actually. So it's a dedicated photonic fixed simulator and design environment. So interconnect, we are having two different type of simulation. One is time domain as well as frequency domain simulations. So we have bidirectional, so multi-mode and multi-channel things are possible with this. We have primitive element library in CMLs, and we have foundry CMLs, as well as we can able to develop our own custom models as well. And we have the one thing is traveling wave laser model, which involves complete numerical tools to develop that traveling wave laser model, and it has integration with their third-party tools like Cadence, Mentor, K Layout, Siemens Tanner, as well as other third-party tools as well. So with this, we can effectively able to develop this electronic and photonic integrated circuits, and it has some advanced analysis like sweep, optimization, and statistical analysis. So this is a numerical photonic Verilog, a runtime library. So this is actually uh, um, a language for modeling advanced photonic components in phase analysis, where complex bidirectional and multimodal and multi-wavelength optical signals are fully supported. So whenever we are dealing with complex photonics components, unlike normal waveguides, see this kind of lasers, modulators, uh, and photodiodes. So this using this modeling language will be very much helpful to do the analysis, and it will support Cadence vector, and it will enable the co-design as well as co-simulation of electronic ICs and PICs. It will provide a variety of active and passive components, passive photonic model templates, and it will support both time and frequency domain analysis as well. And next, Cadence virtuosa plus numerical interpretability. So which means I hope the people, those who are working with electronic ICs, might have heard about this Cadence virtuosa software. Cadence is one of the leading software for developing analog and digital electronic integrated circuits. So integrating numerical with the Cadence virtuosa will help us to effectively develop this electronic and photonic integrated circuits together. So as you can see, within this is the layout, and within here you can able to choose the interconnect simulator. So it supports both frequency domain and time domain analysis, and apart from that we can do the Monte Carlo analysis and corners analysis as well. And next is K layout. KL layout is actually a CAD design software. It is used to design layout for photonic lithography techniques. So whatever we are designing, we have to print it on a silicon chip or like other wafers. For that, we need to design our structure, right? So for that kind of designs, we can use scale layout. So with the help of numerical with the help of this integration with the scale layout, we can able to export the layout to numerical multiphysics tools, as well as we can these process file to construct 3D structures for simulation as well. So with the help of this one, we can directly extract circuit layout netlist to build numerical interconnect circuit schematic, as well as this say within the K layout we can also do the frequency and time domain analysis. Next one is Siemens Tanner. Siemens Tanner is also a one of the electronic integrated circuit software. So this Siemens Tanner having two different editors. One is S-edit and another one is L-edit. So whatever we are designing here and whatever we are designing in this L-edit, we can export these two components directly to the interconnect, and there we can do the complete analysis. As you can see, this is a different module, and this is an electronic IC, and this is the photonic components, and all these photonic and electronic components we can uh, export the design directly to numerical interconnect from S-edit as well as in the L-edit, and we can do the analysis as well. These are the results, like the same thing. We can do the both the frequency and time domain circuit analysis. So this is our schematic editor. of the numerical interconnect. So this is the main toolbar, and this is where our circuit will look like. Circuit will be there, and this is the library area, and this is the element libraries, script file editor. Here, this is for optimization tools, and this is where we can enter the script prompt, like for using the numerical scripting. And this is element tree, and this is for result view, and this is the property view. There we can hover around to see the component properties, as well as we can edit the properties as well. So uh, we cannot able to develop simulate a complex structure within this small time. So for that, I have come up with one of the very much important component of PICs, ring resonator. So many of the people, those who are working in this field of photonics, may get to know this ring resonator. Ring resonator has a wide variety of applications. So it is actually a looped waveguide formed by connecting the ends of a waveguide. So this is the looped waveguide, and they are having a coupling waveguide. So what we will do is, so this waveguide is also called as bus waveguide or coupling waveguide. So the ring doesn't have any openings to enter the inject the light into it. So we can couple the light into this ring structure with the help of these waveguides. These waveguides are called bus waveguides or coupling waveguides. So if we enter the light into inject the light into it, it will coupled into the ring structure in the form of evanescent field coupling, and it will resonate inside the ring structure, and the light won't be completely coupled inside the ring structure. So based on certain conditions, it will allow only the certain wavelengths to pass pass next to the ring. So that is why the transmission spectrum look like this. So as you can see, the transmission profile is frequency or wavelength dependent. So because of this feature, this ring resonator is widely used as in the modulator circuits, filter circuits, optical frequency filters, as well as wavelength selective filters. Even in a division multiplexer also, this kind of ring resonator is used. Ring resonator is widely used in almost all the places. It is one of the very much key component, like transistors in electronic ICs. Ring resonator is a very much important component in photonic integrated circuits. So some of the applications are optical filters, modulators in telecommunications, sensors, frequency comm generation in supercontinuum generation, like nonlinear optics, and also in quantum computing. So in quantum computing, we can generate entangle the photon pairs. So one such example is super wave quantum mixing. That one. Fo- uh, then four-way mixing. Then we can able to develop this quantum logic gates with the help of this uh, ring resonators, and it will act as a single photon source as well. So technically, single resonator is actually a device, photonic device. So this ring resonator can be simulated both on device element level with the physics-based simulation tools such as FDTD or mode, or circuit level simulation like interconnect. So we are going to simulate the ring resonator in the numerical interconnect. So for that, so this is the double bus ring resonator, which means it is having two waveguides on both the ends, and within the waveguide we are having this ring structure. So we are segregating this physical model into different components. There are two straight waveguides here, and there is two waveguide couplers, which means here the coupling will happening, and there are two bend waveguides. Here one waveguide, and here there is two waveguides. So by segregate dividing the ring resonator into different segments, we will be able to effectively develop a ring resonator circuit in the using numerical interconnect. So which was earlier one, but now like in the latest version, you can directly develop the ring resonator using a double ring resonator component, but we are going to do this in the component level, like using only waveguides and waveguide couplers. Let's see how can we do that. So now I'll take you to the numerical interconnect interface. It's loading, it will take some time. So this is our numerical interconnect schematic editor. So at the center you can see this root element. I hope my screen is visible. Can anyone confirm it? So this is where our circuits will look like, and this is our library. We'll be inserting the components into the layout editor from this library as well. And here we'll see the description of what kind of models that we are selecting. Like if I'm clicking the waveguides, you can see the different waveguides that we are having here. And this is the property view. Whatever the components that I'm selecting here, the corresponding properties will appear here. We can able to edit, modify the properties as well. And this is the result view. Once we run the simulation, we will be able to observe the results from here. So now we are going to develop a ring resonator structure. So for that we are going to develop segregate into different segments, and we are going to develop that with waveguide couplers and straight waveguides. So now I went to the element library. Here you can see the waveguides. So I'll start with the straight waveguide. So you can just drag and drop it, or you can double tap it. To double click it, that is one option. Otherwise you can just drag and drop it. So these are the two different ways to insert the component into the layout editor. So now I'm going to rename the editor into straight waveguide 1. You can name it whatever you want. For my reference, I just name it. Here you can see the properties, right? So if I click the straight waveguide, here I can see the name. If I uncheck the anode, you won't be able to see the ports as well as the properties. If I keep it true, you can see the port 1 and port 2, and you can see the properties as well. And what type of waveguide is it, and what is the description and prefix, what is the prefix it had, everything. Here you can configure either it has to be unidirectional waveguide or a bidirectional waveguide. We're keeping it bidirectional, which means we can send the light from both ends. So that is actually good. And this is the frequency that it is going to operate, and this is the length of our waveguide. So here we are going to I'll let you know how to do that actually. And here we are having the what type of mode we have to launch inside this waveguide. So we are having two modes. One is mode 1 and mode 2. So and we are having this orthogonal identifier 1. So based on this identifier, we can able to identify what type of mode that we are launching actually. So for launching a mode, we'll be using the analyzers or the sources. So while using those analyzers, there will be an option to launch the mode that we desire actually. So for the typically for TE modes, we'll be having this identifier 1, and for the TA mode, we'll be having the identifier 2. And the other things are like you just need to keep it a default option only. You don't need to play with the default settings as of now. For the complex simulations only, we need to play with the uh, 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 what do we say that next we are going to import a waveguide coupler. Now I'm going to rename the coupler into waveguide coupler 1. And now I have renamed it to waveguide coupler. So in ring resonator, uh, the coupling into the ring based on two things. One is coupling length and the another one is coupling gap. So coupling gap is actually uh, here we cannot directly enter the coupling gap here in the interconnect. Instead, the coupling gap is actually mathematically expressed as coupling coefficient. So instead of entering this coupling gap, we can enter the coupling coefficient here. So that will determine the coupling gap. So uh, so the waveguide coupler, if you hover this, you can see there is a uh, waveguide input parameter. We have three options. One is coupling coefficient, length, and table. If you are having a table, you can load a file. A lot of files with the data of different coupling coefficients for different values. Here we don't have that. So instead, what we are going to do is we are going to enter the coupling coefficient for the uh, mode 1. Here we'll be going to discuss with TU mode only. So we are going to keep the coupling mode as 0.2. So by changing the coupling coefficient means we are changing the coupling gap between the bus waveguide and the ring waveguide. So other than that, you just need to keep all the things as a constant. And so our straight waveguide, we need to uh, assign the properties for this. I hope you can see this. So here we are modeling this part now. So we have inserted the waveguide coupler here. We have inserted a coupler here and we have inserted another waveguide here. But we have to rotate this waveguide in this particular direction and rotate and we have to create two copies of these two waveguides. So for the coupler we have inserted a coupling coefficient which will allow the software to determine the coupling gap between them. So now we have to insert the properties for this waveguide. So since this waveguide is a straight waveguide, the mode traveling through this bus waveguide will coupled into this and it will travel through this. So we have to give the effective index as well as the group index for this waveguide. So it will help us to determine the mode that is traveling through this waveguide. So going back to the going back here. So now and also we are assuming the ring radius as 40 micrometer. So now I'm going to rotate this waveguide by pressing Ctrl plus R. Now you can see it is rotated. So now I have to determine the length. How can I determine the length? So this entire waveguide, so this entire ring resonator ring structure is segmented into four components, two straight waveguides and two waveguide coupler. So waveguide coupler, we don't have any coupling length. So which means uh, it is completely two total arc. So for a ring, the circumference of a ring, we can say it is 2 pi r. So we have, let's say we have two semicircles. If we are having two semicircles, we can say it is pi r plus pi r, right? So the length of a single straight waveguide is it's pi r. So what we can do is we can change the unit and in the expression we can type pi star. So the ring radius is 40. So which will help us to changing it first. First, before entering the value expression, just make it 0. Now you can enter the expression pi star, the radius of the ring. Actually, it has to convert the unit properly. Okay, let you another. I'll tell you another method to do this. So instead, you can go to the root element and you can see this is an edit. You can click the edit and you can add an additional property. Just type radius here and make this quantity distance, and we are going to keep it 40. Click OK. Now again go to the straight waveguide. So before entering the expression, make the unit in micrometer and keep it 0. Now I multiplied by, so I have to use the percentage symbol on both side of the property name. Yeah, now you can see the length is changed. Now what I'm going to do is I'm going to create copy on each of these two waveguide as well as in the coupler. So I'm going to change its name to side waveguide 2 as well as this one duplicated. I'm going to keep this here. So which is waveguide coupler 2. So now I have created the complete ring components. So now I have to create a connection. You can create a connection either by using the mouse. You have to right click once here and then you have to drag the mouse to the another port, then you can do the connection. Otherwise, if you press alt plus C, you just hover it. Yeah, so you can see your system will automatically detect the nearest port and it will create a waveguide. Now we have created a ring structure. Now what we need to do is we need an analyzer to inject the light into the ring resonator structure. For this, go to the library and here we have analyzers. Click on the optical and we are going to do the optical network analysis. This is actually for frequency domain analysis. We are not going to do the time domain analysis of now. So here this optical network analysis will help us to inject the light source at the desired wavelength as well as it will detect the output as well. Also, with the help this optical network analysis will help us to launch multiple number of inputs. So you can see I can keep it 3. It will give us 3 input ports, two input ports. So as of now we don't require any number of inputs. So I am going to keep it as one number of inputs. So now I'm going to launch the light through this port and again I'm going to record this one here. Yeah, since we are using this double slot ring resonator, we need to extract details from drop as well. This is input port, this is through port, and this is drop port. So I am going to add one more input. Yeah, Now our circuit is complete. The next thing is we have to check whether we have created the property, the input waves and everything as fine. So here we are going to launch the waveguide at the central frequency. By clicking on this unit, you can see you can change the frequency to wavelength as well. If you click the nanometer, you can see it is around like 1.155 to nanometer. So it is okay to keep it at that one, and the frequency range is actually the spectrum broad range, the broad. It is only given as 100 only. So what I'm going to do is I am going to increase it to one more 1000 gigahertz, and the number of points is 1000. So you can increase the number of points to have a much more sharper one, or like increasing the more number of points will give you the better resolution. But as of now we are having a small frequency range. The 1000 number of points is enough, and we are going here. You can see the orthogonal identifier is 1. So what I am going to do is I am going to have this one as my ortho, which means this ONA will launch the TE mode. If I am making 2, the ONA will launch the mode 1. So let's see. So now I'm keeping it as 1. And you can change the label for different modes. You can change the labels. Now I'm going to my straight waveguide. Here I'm going to change the effective index. This effective index is actually indicates the mode confinement. So higher the mode confine, higher the effective index, better the mode confinement. So 2.8 is actually a better effective. This will uh, help us to identify the type of mode we can. You can also use a mode profile analyzer at this end to analyze the modal analysis well. So now we have done everything. Again I am going to change this 2.8 to 3.9. Yeah, now we are going to run the simulation. Yeah, since we have done it completely, the simulation ran without any errors. The simulation completed successfully. Now in order to identify results, so these are components. Our components won't be having results. So this is our analyzer. So our analyzer will be having the results. So go to the elementary, click on this ONA. Now come to the result view. Here you can see for the input 1 we are launching the light, right? So for this, the transmission, we are, see, now we got the transmission. So which is a transmission spectrum that we are able to observe in the for the ring resonator, which is similar to that of that. Now we'll keep the layout. We don't close this visualizer. Now what we will do is we'll try to launch the different mode. Let's see how our results vary. Now again, so you cannot now go to the straight waveguide. Try to edit the effective index and group index in the property view. You cannot edit it. It is because it is in layout mode, so run mode. So you have to switch to design mode. After that only you can edit the properties of the components. Now I am going to make it 2.8 and 3.9. Similarly, for the other waveguide also do the same thing. Yeah. Now we have changed the mode to effective index and group index. Now go to the ONA. Here you can see the orthogonal identifier is 1. Now what I am going to do is I am going to change it to 2. Now the orthogonal identifier is 2, which means now our ONA will launch the TM mode into the waveguide. Now rerun the simulation. Yeah, the simulation is completed now. Now if you add this to visualizer 1, now you can see using a different mode we got a different results. Yeah, That's it. Apart from this as well, you can also able to see the loss, dispersion, as well as you can able to identify the free spectral range as well. Free spectral range is nothing but it is actually the distance between the two waveguides, two resonant peaks. So at this wavelength, the free spectral range is this one nanometer. You can able to see the quality factor as well. Quality factor is something which is a ratio of full width of maximum versus the ratio of resonant wavelength to the full width of maximum. You can able to see the quality factor as well for the this transmission spectrum. Yeah. So this is the simple simulation of a ring resonator. So as what we did is we divided the double bus ring resonator into different components, and thereby we modified the uh, different component properties inside the ring resonator. Then we developed a circuit, and we analyzed the results. So this is one type, and the next one is we are going to develop the ring resonator based on parameters that can be extracted from classical behavior analysis. So previous demo, what we did is we directly enter the parameters. So the coupling coefficient, or else the effective index, or the uh, a group index, we directly entered into the numerical file. But here, what are we going to do is we are going to create a coupling region in ANSYS FTTT. From there, we are going to extract the coupling coefficient, and we are going to extract the effective index as well as the group index using this ANSYS mode solver, and we are going to import these two properties into the interconnect. Then we'll be analyzing the transmission spectrum. Yeah, let's see how we are going to use it, how we can do that. Yeah, this is the interface of our FDTD solver. So here we are going to design a coupler region. So the coupler region consists of a straight waveguide and a vent waveguide. First, we'll try to create a straight waveguide with the thickness of with the base width of 1.05 micrometer and the base height of 0.5 micrometer. Could you please confirm whether you are able to see the screen? Hello, anybody there? Yeah, okay. Yeah, thank you. Thank you for the confirmation. Yeah, let's create the straight waveguide. So I'm gonna name this as outer waveguide. As I said, we are going to have the base width of 1.05 micrometer and the height of 0.5 micrometer. Now, these vertices are actually allow us to consider these vertices are actually the points of a straight line which are traveling through this waveguide. Now, for modeling a straight waveguide, you don't need to have you don't need to have more than 2 points. Now, since we are modeling an outer waveguide, we can remove the 2 points. We need to mention only the start point and end point for a straight waveguide. So we are going to start at 0 at x and use 7.45. and the length is 150 micrometer, and again it will be at 57.05. So you can keep this at 0 as well, but I am not creating the waveguide at the origin. So you can create the waveguide at the origin as well by making this y vertex a 0. Now, once I have fixed the geometry, the next thing is we have to assign the geometry for that. So here we are going to here you can see we are having a inbuilt material library. These are the different material models that have come with Lumerical itself, Lumerical FTT itself. Additionally, you can import the materials. Uh, so now I'll tell you what to do. So now you can see I have imported I have inserted the material. Now if I click apply, now I am not able to see the waveguide. So what I can do is I can click the zoom extent option. Now I can see the straight waveguide. So here if you click this database, here you can see the different material database. Here if I want to add a new material, I click this. Here you can see what are all the different type of materials that you can add. NK material, which is not a wavelength dependent refractive index. You will be having only one value, one N value and one K value, and analytic material, Chi2, Chi3 Raman square, and conductive materials as well. D by dielectric materials. Instead of using the refractive index, you can use the dielectric constant. Index perturbation material, which is actually a refractive index varies when there is a change in temperature. Those are called index perturbation materials, and non-linear materials like non-linear materials, Lorentz minerals for specifically for plasmonic materials. And we are having different. And if you are having a material data in the form of wavelength, N and K values, you can also import those materials using these two sample 3D data and 2D data, and Selmayr equations are also you can import it. So these are the already available materials. You can also import the materials. You can give them a name, and you can give the mesh order, and you can give the color and what kind of type as well you can give it. So now I have designed the outer waveguide. Now what I have to do is I have to create the arc for the coupling region. So for that, what I did is break down that coupling region into three components, two arcs and one straight waveguide. So first model the straight waveguide, which will act as the coupling wavelength. So the length of this waveguide is actually the coupling waveguide, coupling length actually, inner waveguide. So the thickness, height. Now this is also a straight waveguide. We don't need vertices more than 2 points. So here, what I'm going to do is I'm going to start at 35 and end at 35. So 115. So 35. I'm going to assign the material as, yeah. Now you can see there is a gap. This is called the gap between these two waveguides is a coupling gap, and this is the coupling length, which means how far the coupling waveguide is actually interacting with the ring structure. So this is actually the component of our ring structure, but here it is not a conventional circular ring. Instead of that, we'll be using the racetrack resonator, like racetrack type of ring structure. So for this, the coupling wavelength starts from here to here. So the coupling wavelength is actually here. So we started at 35 and ended at 115. So we have the coupling wavelength of 80. Next, we are going to model the arc on either side of this waveguide. So let's do that. So I'm going to start with arc on the right side. So the same procedure, base width. Yeah, now here we need more than two vertices, 2 points actually, more than two xy points. So for modeling a straight waveguide, having 2 points is more than enough. But since we are going to model an arc, at least we need 3 points. So here we are going to model the arc with 4 points. So we are going, since we are going to model this right arc, so this side, so this will be the 115, and this is 35, then 34, 317, then 35, so 150, 317. So now assign the material. Yeah. Now you can see have made the arc on the right side. So this is completely involves this uh, uh, imagination and the how those mathematic things work. If you know those things, it will be easily able to model these kind of structures. Apart from that, you can also develop if you are good in CAD designing, computer aided designing. So if you are good at using some 3D softwares, what you can do is you can create this kind of structures in the 3D software. Then you can import these structures. You have the option for that. You can import the STL file. uh, as you can see, import CAD objects from an STL file. So you can develop a 3D file over there in the CAD software. Then you can export into STL file, and you can import the STL file into the numerical. So you can do in that way also. So now we have to model the left side arc. So I'm going to first I'm renaming it arc left and the base width 0.5. So now the left arc to start the 0 0, next 0, 19.3. Actually, I forgot to change the base angle degrees to 90. 90 means the waveguides are like straight at the edges. So we have to develop we are developing that kind of waveguides only. So I forgot to check that. Please check base angle degrees. Let's make it to 90 in all the other waveguides. Okay, now I made 90 everywhere. Now what I'm going to do is I'm going to add all these waveguides into a new group, and I'm going to name it as coupler region. Now I have created this coupler region. I need to create a substrate where it has to reside on. So for that, click the rectangle. So this will be our cladding. So we start as minus 2. So for the cladding, we are going to take silicon We are going to overwrite the shadow. Already I have given the same material. Yeah. Yeah. Now we have assigned the we have defined the structure. Now what we have to do is the next step is to add the solver. So what we are going to do here is we are going to identify the coupling coefficient in numerical MTTD. So for that I have ordered the solver. So you can change the geometry of the solver so that it can align perfectly within the texture. So geometry, I'm going to 7.5 and 42.5. From the settings, I'm going to keep the default only. You don't need to change anything. And we are keeping all the boundaries as PML. PML means perfectly matched layers, which means by applying these boundary conditions, it will absorb all the incoming light. It won't account for the reflection. So PML is actually the most common boundary condition which will be used for all kind of like most of the simulations. So now I have and keep all the things are like default settings only. Yeah, now we have added the MTTD. Now we have to, in order to find the coupling coefficient, we need to launch the source from this end, and we have to calculate the reflection from this end or that end. So for that, I'm going to add a source. So for that, what I'm going to do is I'm going to add a port source. So as you can see, this is the port body. Within this, we'll be having ports. So I'm going to increase the frequency points to 20. So having an higher frequency points will give you a better resolution, but it will also increase the computation time as well. So I have to keep it in time. Keep that in mind. So now I'm going to keep the start wavelength as 1.5, which is in the telecommunication wavelength, and 1.6 as my stop wavelength. So apply this. That's it. Now we have uh, set the basic group settings. Now we have to uh, edit the port. Now top right. So since this is a straight waveguide, you don't need to do anything in the geometry. So what you have to do is you have to align the port at this point. For this, align the 10 point 5. Now you can see that the port is aligned at this end. Now I'm going to increase the port profile samples to 3 till it will increase the resolution, and I'm going to look for the fundamental TE mode. Now you have to check this one. Injection is along the x-axis and direction is forward. So you can see there is a small the purple arrow. That purple arrow indicates the direction of mode propagation. Now let's visualize the mode data. If you click it, the solver allow you to see the mode. Now you can see the mode inside the waveguide. So this mode is actually good only. It is confined well within inside this straight waveguide. Now we can proceed with the further simulation parameters. Now I'm going to click OK on it. What I'm going to do is, you can see if I zoom it, you can see there is a purple arrow. This purple arrow indicates the port which is going to inject the mode, and this purple arrow indicates the direction of mode propagation. Now just click duplicate, edit, rename it to top left. So just modify this 37.5. Yeah. Now you can see uh, the green arrow and the red arrow is pointing towards this direction, which means the mode is traveling in this direction. But actually, we are launching the mode from x to from positive x to negative this direction in the positive x-axis. So what we have to do is we have to change the direction to backward. So which means so this indicates that the mode is traveling from this end of the waveguide to the this end of the waveguide. Now we have to keep the modes to analyze the mode traveling through this uh, uh, bend waveguides. So for that we are going to add two more ports. So click duplicate, edit, so name it as bottom left. So keep it as 35. 40, and 27. Yeah. Now you can see it is almost aligned with the it is aligned at the center. So here what you have to do is you have to uh, tell the solver that this portion is actually a bend wavegate. For this you have to click this checkbox, and here we are assuming the bend radius as 10 micrometer and the rotation is minus 45 theta. So as you can see, the port actually rotated along the direction of along across the cross section of this bend waveguide. Similarly, copy this top right and type bottom right. It is all and change this to bend waveguide and micrometer and orientation is 44. Since this is rotation in anti-clockwise, like we have to keep that as a minus 45 and this will be in clockwise. That's why we have made this only 45. Now if you zoom it, this is not aligned at that place, so try to reduce it further. Okay, yeah, now it is at the point. Now what we have done is we have created the complete setup for calculating the coupling coefficient. So this model will launch the light from this direction and it will get coupled into this, and we can get the output spectrum here. So if I click run, this simulation will take some time to uh, complete it because it is actually a FDTD 3D simulations. Usually 3D simulations will take a lot of time. So for that I have already have a simulation with the results. So now I'm going to open it. Yeah, here I have the results. If you can see, if you click the port, here you can have the visualize option like your S parameters. So this is the S parameter, and click the absolute square, will give you the S parameter, and So with this, I have to extract the coupling coefficient. So numerical allow you to extract this kind of coupling coefficients from the S parameters with the help of numerical scripting. For that, we have written a script. So what I'm going to do is I'm going to import the script into the script file editor. I'll just hover you through the scripting, so which will be very similar to like any other codings like Pythons as well as MATLAB. If you're familiar with MATLAB and Python, it will be easy to understand. As you can see, this get result is actually the not syntax of this numerical scripting. FDTD ports bottom right S. So from the bottom right S, it will extract the S parameter, and then it will do the absolute square. It will give you the power coupling. So with this, it will extract the frequency separately, and you can save the file here, and it will write the coupling coefficient like wavelength, sorry, frequency as well as power coupling in the x and y subsequently. So now I'm going to run the script. So this script will plot the coupling coefficient for the wavelength starting from 1.5 to 1.6. 1.6. So now the coupling coefficient is also saved in the same folder. So what we are going to do is we are going to import this coupling coefficient into the numerical interconnect. Now we have completed extracting the coupling coefficient. Our next step is to do the model analysis for the waveguides. Now we can close this. Now what we are going to do is we are going to do the mode properties of the passive straight and bend waveguide. For this, click the mode. So we'll do the model analysis because so it is okay to have only one waveguide, the cross section of a straight waveguide. So from that itself, we can able to do the model analysis. This is the mode finite IDE layout. So click the structure. I can edit. So I am going to type the code. This will be the uh, core for material. So for the we know that the core thickness is sorry, width is actually 1.05 and the height is 0.5 micrometer. So we are adjusting this pi minima and maxima in a way to keep the expand. Look at the expand now. It is 1.05. So now we are going to change the y min equal to. Since we are focusing on the cross section, you don't need to worry about the z span as of now. So yeah, now we have inserted the core. Now we are going to insert the cladding. So for that, just rename it as rectangular slab. So x min is equal to 5 minus 5. Excuse me, give me a moment. Yeah, hello. Sorry for the interruption. So, it's 5 0. So the material will be silica. So that's it. Now we have created our cross section of the straight waveguide. Now what we are going to do is we are going to add the mesh. So meshing is nothing but it is actually allow the solver to solve the equations at a very small regions. So it will help you to have a better resolution. So what we are going to do is we are going to, since we are doing it only for the cross section, not in the 3 dimension, so it is okay to have override the mesh in the x and y axis. So we are going to keep it like this. And here, if you see the geometry, you can directly type the geometry values for the mesh, or else you can click this based on a structure. Since we are going to calculate the mode at the mode at this core region, I can type the name of the geometry. Yeah, we click apply. Now you can see that the mesh is applied to the core, but you cannot see the mesh. So if you want to see the mesh, what you can do is you can click the mesh button, but you can see the simulation mesh once you add the solver region only. So now we have added the simulation region. Now we are going to use we have to add the solver region. So now for the solver, I'm going to keep the background material as 1.44 like, and minus 1.5, 1.5. So keep the mesh as a I'm just trying to keep the mesh settings as like higher, so it will give us the better results. So now if you zoom it, you can see the meshing. So in the added the mesh region, you can see the mesh has been overridden, and here you can see this place mesh is actually equivalent. It is not overridden by the mesh that we have added. So now we can click the zoom extend. Now what you can do is you can click run. So it will open a eigen mode solver analysis like this. Here what you are going to do is I am going to keep the wavelength as 1.5. I click the mesh texture. Yeah, now you can see it has given the texture. I click the calculate modes. So you can see it is calculating the modes. Actually, I have added a finer mesh. I think that is why it is taking more time. Let me terminate this and now you can see the mode for the particular wavelength. What you have to do is to click this frequency analysis tab, click on the track selected mode, detailed dispersion calculation. You have to keep the number of test modes as 1, that will be fine, and the number of points as I'm going to keep the stop wavelength as 1.6. If I click the frequency speed, it will calculate the frequency speed for the wavelength that we have selected from 1.5 to 1.6 with the number of points of 10 for the selected mode. This will calculate only for the selected mode. What I do is like I'll just stop it. Problem is I have added much finer mesh. So you just disable it. It will take some time. So we don't have enough time. You just disable this. So I'll rerun this. Structure, calculate modes. Yeah, now this won't take that much time. See, it is almost giving the same results. So now, you click the frequency sweep. It has to sweep it fast. Now we have the results. If you click the frequency plot, you can see what are all the results that we got. We have effective index, loss, gain, group index, group velocity, and every details. So you can export all these data to interconnect. So for that, what you have to do is you have to click the data export option. As you can see, to click the LBF file, and you have an option for interconnect export. So if you click to export interconnect, so you can export the data here. So I have already exported the data here. Let's for the straight waveguide. This is for the straight waveguide, because our component has both the bend and straight shapes, right? So for the straight waveguide, we have done it. Similarly, what we have to do is we have to do the model analysis for the bend waveguide. For that, we have to keep the bend radius as 35 here. Like we'll just try to keep it at 35, and for that we'll calculate the modes. Again, we have to do the frequency analysis for this mode as well, for the bend waveguide. So in a similar way, so this is what we have done it for only one mode. So what you can do is if you hold the shift and arrow button, you can select multiple modes and you can uh, do the frequency sweep for all the modes. So that will take more number of time. For that we have did it for only 2 modes only. Now what you have to do is you have to export the data the same way. Export for interconnect. Now we have exported for the bend waveguide as well. So now we have exported the model properties, mode properties from the mode, as well as the coupling coefficient from the numerical FDTD. Now what we have to do is we have to create a ring resonator. So now we have to calculate the import these values that we have taken from coupling coefficient from utility and uh, mode properties from mode into the interconnect to calculate the transmission spectrum. So as we have already created a ring resonator structure, I won't be
Jay
going through
Krishna,
the. Yes, ma'am. Yeah,
there
yeah.
is some background noise, I think, some ringing of something.
Is it now?
No, no,
Are you
it's not
hearing now?
there. Okay, okay, thank you. Please continue.
Okay. Yes, yes, yes. So now I'll go to like at a faster pace. I think we are running out of time. So in a similar way only that we are going to create a structure, but instead now I'm going to add a waveguide. So here you can see previously we added only straight waveguide. Now you can see there is an option called mode waveguide. So here we have to add this mode waveguide. So this waveguide will allow us to import the data from the mode solver. So just name this waveguide to straight waveguide 1. Now click the waveguide and you can see its properties in here. Now I am going to keep the length at 0 only, since because it is the waveguide where I am going to launch the light source. So I don't need this to be very much long as well. So here you can see there is an option called load mode profile true and load profile file true. If this checkbox is not true, we cannot load the LDF file that we have calculated from the mode solver. So now click the LDF file open and go to this I have, since this is a straight waveguide, I have to, now I have uploaded the property. So that's it. So this is for the straight waveguide. Now what I am going to do is I am going to import the waveguide coupler. So click this. So import the waveguide coupler. So now just rename it to waveguide coupler. So now here what we have to do is we have to import the coupling coefficient. So in the previous case, what we did is we directly entered the coupling coefficient for the mode 1 and mode 2. But here what are we going to do is we are going to import the extracted the data from the FDTD, right, for from 1.5 to 1.6 micrometer. So we are going to complete data. So for that, just change the input parameter to table. Now so you can see the load from file option check isn't false, just make it true. So that will allow us to import the file. So now, so here we have the coupling coefficient. So since we have calculated for only one mode, so it is enough to load it in this mode 1 only. You don't need to do it in mode 2 because we haven't calculated for it. So yeah, that's it. As of now, yeah, now we have imported the coupling coefficient and as the mode. So now this data allow us to um, allow our solver to predict what kind of mode that we are going to launch into our waveguide, and what will be the coupling gap. So now we are going to add two more waveguides to uh, make the solver to understand how much bend it is and how much coupling length that it is having. So before that, go to the root element, edit it, and add two properties. What are we going to do? Add is we are going to add radius. So the radius is actually, it change this to distance. So 35 micrometer. Now we are going to add one more property, which will be coupling length. So distance. So we are going to have the coupling length of 80. So that's what we written FDTD. So we are going to add it. Yeah, now we added it. Now we are going to add one more straight waveguide. Sorry, mode waveguide. So because this straight waveguide is actually the coupling region of the entire racetrack resonator. So if you see these straight waveguide, so we are going to model this straight portion now. These two straight portions, because these two waveguides determine the coupling length. Since we are talking about this racetrack type of ring resonator, we are going to model that one. So now we are going to import the, we are going to change the wavelength. So what are we going to do is in the expression, since this replicates the coupling region, so we are going to type the coupling wavelength, coupling length, and it has to be 2 times of it, because on either side, one which will be closer to the waveguide coupler and other will be here. So this is the coupling region. Now you can see the length is changed to 160 micrometer. Now we have to load the LDFN. So side waveguide. Yeah, now it is loaded. Now what I'm going to do is I'm going to rotate this wave actually. Yeah, done. Now I'm going to add one more wave. So which I'm going to name it as bent wave. So this will replicate the all the bent in the ring structure. So all the bent in the rings. So the part of the ring is made up of the straight waveguide and the bent waveguide. So the straight waveguide is 160. The whole ring is 35 micrometer. So what are we going to do is we are going to type full star radius. So this will create the pen waveguide and rotated it with the Ctrl plus R using. Now I have to add one more thing, which is actually the file mode data that we have calculated from the model analysis. Yeah, now we have added all the properties. Now what we have to do is we have to make the complete the circuit connection. Yeah, now we need to add the analyzer for launching the mode. So again we are going to add the optical network analyzer. So input to this straight waveguide. Now output to this port, and again check the ONU. So now this time we are going to type start and stop. So start frequency, instead of using the frequency, you are going to use the micro 1.5 and 1.6. I'm going to increase the number of points to 1 lakh. It will give us the better resolution. Yeah, that's it. So keep the all the things same. Now what I'm going to do is we're going to end the simulation. Yes. Now the simulation completed successfully. So click the ONA. Yeah. Now you can see there are more number of takes, but is actually this is not the actual result. This might be due to some mode mismatch, but I have already the results, the like simulated results. Let me show you that one. So yeah, you can see the transmission is here, which is similar to what it is here. You can see the transmission, right? So which is similar to that one. And if I am able to zoom this picture, zoom this particular depth, so you can see this is similar to this one. So now this mode is actually similar to what we have seen in the mode solver, and as well as the complete coefficient is also similar. So this is another way of developing the components separately in the other solvers in FDTD or mode or in the multiphysics solvers, then importing those data into the interconnect directly, then analyzing the circuit simulation in the interconnect. So with this, we have completed those two demos. So as of now, I hope that you might have got to know what are all the capabilities of numerical tools and what can we do with the photonic. How can we simulate the simple photonic integrated circuit with this numerical tools. So as we don't have enough time, we won't be able to show the complete tools capability. We are left with this numerical multi-physics and other tools as well. Yeah, so I hope this would have been a wonderful, a better session for you. This would have improved, like give you some idea. I hope so. The next, we'll wind up the session with a case study. The Compound Tech is actually one of the foundry processor, which means they are making ICs for big companies like Nvidia, Apple, Samsung. So having a successful partnership with Numerical, they were able to, do the develop a silicon photonic grating coupler with a 20 times smaller footprint than the previous coupler and with the improved performance. And also within a 2 weeks, they were able to optimize the designs for 8 manufacturable variants that have been developed. So this is one such of kind of an example that even leading industry foundry experts as well are also using this numerical simulation tools as well. So numerical tools has a lot of capabilities. So this will be helpful, useful for your research as well as for the industry simulations as well. And also this ANSYS numerical cloud features are used to scale as well as it will help you to accelerate the design effort. It will help reduce the time to market as well. So with this, I'll wind up this session. Thank you for patiently listening to the session. Thank you. If you have any doubts, like you can ask me, or else like if you have further doubts, you can write an email to this. Here is the contact number as well as the email ID.
Yes.
Yes.
Thank you, Jay Krishna, for such a wonderful session. The
Yes, thank
students
you.
have a very good idea about this year. Now,
Yes.
this one question that I have is that when we are simulating these photonic circuits,
Yes.
so when we have these foundry ka PDKs, and there are
Yes.
some components, inbuilt components, right?
Yes.
They have the ready-made components. So
Yes.
how can we get those components in the means those parameters, those characteristics of the component in these circuits when we simulate? Because here we have a modulator like you, or you have a beam splitter or some component.
Yes.
How
Yes.
can we simulate that PDK ka component here?
Yeah. For that, we need to have some other libraries, like as I shown that Vertigo library and CML compilers, right?
Hmm.
So as of now, like since I have recently joined, I don't have the accessible to those libraries,
Hmm.
CML compilers.
Okay.
So with the CML compiler, you can log in. As of now, I don't have license to Q interconnect and CML compiler.
Okay.
So those two for simulating the quantum computing, like
Huh.
much more quantum solvers. Like you can use Q interconnect, which is actually within this interconnect solver. But
Okay.
instead of this, we are working on it. So once we got this Q interconnect as well as the CML compiler, you can get these foundry models from the CML compiler and can directly import into the interconnect. Apart from that, you can interact with this some other electronic ICs as well. Like I said, like Siemens Tanner, the CAD and Switchosa.
Hmm.
So from there also you can directly import it.
Yes.
Yeah.
Okay.
Yes.
Thank you. Thank you,
Yeah.
Udna. Thanks for your time and patience.
Yeah.
Really.
Thank
Okay.
you. Thank you.
Thank you. So we'll close the end for today. Tomorrow
Yes.
again we'll meet at 10 o'clock. All the participants, online and offline. Okay. Thank you. We'll
Yeah.
end the
Thank
meeting.
you. Yeah. Thank you.